Hello, hello. All right, this is 1.3. We are looking at characteristics or attributes of graphs of functions. So we're talking again about functions where each x has only one y. So each x has only one y. So we're not looking at circles, we're not looking at things that cross back and forth, just functions that are clear and kind of moving in one direction. And we're going to talk about increasing and decreasing functions. Those are two vocabulary words we'll talk about. Also relative minima and maxima, two more vocabulary words. And finally, even and odd functions, just vocabulary today, no actual working of numbers or math. So these are pretty obvious, but I'm going to go through them just quickly. A function is increasing, so we say a function's increasing if the graph is rising from left to right. So if the graph is rising from left to right. So if I look at this graph, I'm moving this way, and I can see that if I start at my original point, my graph is going up at the beginning, and then it's going down, and then it's going up. And so we would say that this section where it's going up, this section, the function is increasing. It's increasing all the way up until it meets our top, and it's increasing all the way from the bottom. And I can also look over here and say, now it's going down, it hits the bottom, and from this point forward, my function is also increasing again, and it's going to increase forever. So we're just talking about whether the slope is positive or negative, really, at all these different points. Similarly, decreasing means that the graph is falling from left to right. So all these points in the middle where our graph is coming down as we move across, these are all areas where I'm going to turn it, decreasing. So that's pretty straightforward. Increasing where it's growing or getting positive, decreasing where it's getting smaller, increasing where it's growing again. When a function changes from increasing to decreasing, so on my graph it's here, I'm moving on increasing, and at this point right here at the top, I'm changing from increasing to decreasing. We call that point a maximum. It's not the whole maximum of the whole graph, because obviously these points over here are higher. So we call it a relative maximum, which just means that in its little area, it's the highest point. So this is our maximum or a relative maximum. Some people use the word local instead of relative. They say local maxima, relative maxima, same thing. As you can expect, when the function changes from decreasing to increasing, we will get a relative minimum. So this point right here, the function's decreasing, it bottoms out. Where it bottoms out, we call this point a minimum, and because it's not the lowest point on the whole graph, we call it a relative minimum. Just means that in its own little area, its own little corner of the graph, it's the lowest point there. Perfect. So when we deal with relative minimums, increasing, decreasing, we're always looking at graphs and highlighting pieces of them. So it's not a thing where we're going to look at the equations, just where we're looking at our graphs. The other two words we use a lot with functions are some functions we call even and some functions we call odd. So even functions, that's this. It's kind of hard to see these, but my red line is an even function. And even just means that if I drew a line up and down on the y-axis, that I have a symmetric graph. So whatever's true on this side is true on this side. Or I can think about it like I could fold it over and the graphs would match. Or like I could place a mirror in the middle and the graphs would be the same. I like to check by just picking a point on this side and making sure that there's an equivalent point on this side. So that's an even function. This one's also even. You can see here, we've got a mirror down the middle, and for every point on this side, there's another point on the other. And even this line, it's hard to see, so I'm going to make it a little darker. This line is technically an even function, even though it's boring, because for each point over here, there is a point over here. It is perfectly symmetric. Odd functions are not the opposite of even, they're a different thing. And odd functions are essentially where they're symmetric across the origin. And that's a hard thing to imagine because we're really trying to like reflect something over the point in the middle of the graph. And so I actually think about this usually as it's rotated 180 degrees. So we pick up our graph, rotate it 180 degrees and plop it upside down, and we hope that it is the same. So you can see that this, if I rotated this graph down, it would line up exactly on itself again. And one way we check that makes it odd. One way we check it is we pick a point. This is the point 1, 1.5. And the exact opposite point should exist. And it does. So -1, -1.5. So if that's true, if for every point we have like the exact opposite point, both negatives, then we have an odd function. So this is also odd because I can take this point here, which is about 350. And I know that I also have this point down here, which is -3, -50. So as long as that's true, I've got those opposites. This is an odd function. I can rotate it around and see it. Lastly, I have this line. It's also kind of hard to see, so I'll draw it on. This line is also technically an odd function because this point is going to rotate down to here. This is 4, 4, and this is -4, -4. So exact opposite points. Now, unlike numbers, not all functions are even or odd. Most functions are neither. So most functions are neither even nor odd because most functions are not symmetric, right? These are very rare. And so here's an example of a function that's not even or odd. Even though it looks a lot like this one goes through the origin. This one does not. So if I pick a point, I'll check first for even. If I pick a point, even would mean it's reflected this way. Clearly it's not even, it didn't have a reflection. And odd would mean if I take this point, which is 4, 4, that the point -4, -4 would be on my graph. Clearly that's not on my graph. So this is neither. This functions the same way. This is my origin. I can check first for evenness. So I'll take this point here, or let's say I take an easier point. This point here, is there the same point on this side? Absolutely not, so it can't be even. And then I can take this point here, this is the point 5, 3, and say, does this point, -5, -3, does it match? And it does not. So this is also neither even nor odd. We're always looking with even and odd for really symmetric looking graphs, really clean, easy, usually located centered on the origin, centered on that 0, 0. They're pretty darn rare. All right, that's it for this one.